set up the spirit of why we are doing this. So let me quote something very interesting here. Physics means everything to him. I want him to be happy. I want you to set him a goal, something easy enough for him to finish before he dies. So this was a request made by a father who had a terminally in son suffering from a very deadly disease, which was soon to take his life as per the doctors. And to this request made to the PhD guide, the guide replied, "My students and my science are everything to me. I try to be true to both, which is why I can't do what you asked me." Dr. Hawking. The student was Stephen Hawking, and the PhD guide here was David Sharma. So, this is one of the most profound relationships of mentor and mentee. And what Stephen Hawking ended up achieving in astrophysics was David Sharma and Roger Penrose. So, from my own personal journey and from a lot of other people I know, mentorship is possibly the most important thing that could ever happen to someone. So, there can't be a better thing or a better fortune than having a good mentor in life. And with
Yes.
that spirit, myself, Nitesh Pandey, I'm a researcher with Indian Astrobiology Foundation and also the founder of Solitera Scientist. Would like to mentor the next generation of leaders of science in astrophysics and astronomy. And as far as I have seen and interacted with people, I haven't come across someone who is as passionate as Raviji in terms of promoting science and sharing the opportunities related to astrophysics and astronomy to the wider audience and students who are ready to make their career in this field. So me and Raviji discussed to start this initiative where we would sort of handhold and try to mentor the most genuinely interested students who want to dive deeper and make a career in this field so that we could have more future. So thank you so much to Raviji for taking this initiative with me, and I would ensure I would like to request everyone to take detailed notes and uh, make sure that you take the best advantage of this. And as time goes with future workshops, we would be diving much more deeper, as this is the first introductory. So I welcome you all. Thank you so much for giving your time and taking part in this initiative, where we try to share the baton of awe of science that me and Raviji have felt all our life. So with that, we start with Vinayji and Raviji.
Yeah. Just a second. Yeah. Uh, Good evening, everyone. So today we are here to um, have a good evening where we try to share whatever the knowledge we have gained throughout our research. But I would like to share something with every participant here. So we have planned this session to be as basic as possible. That's the reason we have put it as an introductory session. So what I request is maybe some of you might have learned many of these things earlier, but whatever the request we got, it has school students, college students, and some amateur astronomers and general science enthusiasts. So we want to keep it as basic as possible. Maybe you might have gone through some of these tools already. So so what I request is, so just have some fun. Like if you want to share something, you can share with us. And I request everyone to learn something from this. It will be really interesting, and we try to keep it traditional only. Before jumping into the modern techniques, we want you to just get to know about traditional techniques, how we have started our research, and generally how still um, most of the supervisors expect you to start your research work. Okay, though there are many tools, AI tools and all recent days, but still traditional tools are known for their reliability. We should not forget that they are still very much important, significant, and also they are very known to for their preventability also. So they are very reliable. So that's the reason we have chosen all these tools to give a short introduction to each of them. Maybe near the upcoming workshops, we will be choosing a particular data. We will be working on some data sets, okay, using different tools, where we include some of the AI tools also, like how to retrieve light curves from different databases and all. And we are we are also looking forward to provide some internships to some of the students who are like really want to work on some project works. So we are ready to do that. But what we expect is, so whatever you are going to learn here, it is a basic thing. So treat it as a basic. So try to build your basic strong. So that will really help you. So if you have any questions, you can, we have a chat box here, so you can leave your questions there. So whenever possible, we will try to answer those questions. So let us start our session today. So let me share my screen. Yeah, I think everyone can see my screen, right? Is it visible? Yeah.
Yes,
So,
yes.
yeah, I'm Ravi Raja. So I'm currently working on my PhD thesis work. So I actually, again, I have my colleague here who is also a PhD scholar. So he's Mr. Vinay. So we both are like founders of Astro. So our focus is to try and encourage students to do research, and we generally do outreach very frequently. I'm a science communicator and writer too, and a national coordinator, astronomers for Astronomers Without Borders. So let us start our session today. So don't think that it is like very basic. Yes, we have designed it to be very basic. So if you feel something about, don't worry, you can explore it anytime. So we are like focusing on those students who are completely new to astronomy. So bear with us if you are already into astronomy and if you know many things. So let us allow them to learn. Okay. Yeah. Thank you. So let us start today's session. So let us start with, what are we going to explore today? So we have partitioned today's introductory session into four parts. We have observational astronomy, where I will try to just a second, I will hide it. Yeah. So where I will try to give you introduction to telescopes, what are the different astronomical tools we have, and how to actually observe the sky. Then following, we have positional astronomy, where I introduce you to different coordinate systems and what is the Julian date, and what is heliocentric Julian date, then what is barycentric Julian date, and how to target different objects using seasonal constellations, which is very much important for any observational astronomer. Then we have practical astronomy, which is dealt by Vinay Kumar. So he will be dealing with what is black body radiation, and what is how to collect a spectra, and why a spectra is important for us, and what a spectra reveals basically. And then not just that, we will try to give you a short introduction about magnitude systems and how we estimate temperatures using colors. Anyways, we will be exploring each of these topics in detail using various tools in upcoming workshops. Don't expect like us to cover everything in detail now itself, because this is just an introductory. It will be too much for you too. So that's the reason we try to give you a short introduction about each of these topics. And in upcoming workshops, we will try to elaborate each of them, where we introduce you to different software, different AI tools, where you can make use of real-time data and explore it. And the last portion is practical astronomy, where I try to give you introduction to different astronomical databases, how to collect the data. And Vinay will be introducing you to PyRAF. IRAF, he will be explaining why it is important, why is it significant, and how to reduce the data making use of PyRAF or IRAF. Now we have different other tools too, but still why we have chosen some traditional tools here is, so because of, as I mentioned, because of their preventability and reliability. So that's the reason we have chosen here. And then we have extracting light curves and classifying variable stars. That too we will be dealing in detail. So here I will be giving you introduction. So in next sessions, we will be going discussing it in much detail. Now let us start our session for today. So before jumping into like much detail, so I just want you to give a rough introduction about astronomical telescopes. So every one of us know that telescopes basically detect radiation. We have different types of telescopes: radio telescopes, space telescopes, ground-based telescopes. Again, we have optical, we have infrared. Then we have space-based telescopes, which mostly observe in ultraviolet, X-ray, and gamma ray radiation. So all these telescopes' job is to collect light from the celestial object, and they give us information. Okay, whatever the light we receive, we try to interpret. whatever the information we got from that star or any celestial object. We try to determine its temperature. The main purpose of collecting data is this, to interpret the temperature, to measure its period. If it is, in the case of binary system, period plays a very important role. Even if it is a single star, its rotational period also is one of the important thing. And not just that, we can also estimate the chemical composition, like what is the chemical composition of that celestial object. And by collecting repetitive spectra, we can do Doppler studies also, where you can measure radial velocities. So each and every like the data we collect from different telescopes, each and everything have some application which are extremely important to understand the nature of that celestial object, and in turn to understand the universe too. So now I just want you to show something interesting. This is multi-wavelength ground and space-based observatories. So depending on the purpose and necessity, each and every astronomer choose a particular telescope. So basically, myself and Vinay, we generally work in optical and infrared. So we basically collect data from Hanley Telescope, so which is Indian Astronomical Observatory, and we also it is also called as HCT, Himalayan Chandra Telescope, and we also collect data from VBO, Vainu Bapu Observatory. So we collect spectroscopic data and photometric data, and we try to analyze it, reduce and analyze it. So we basically work on closed binary stars. We try to understand the nature of those binaries and how do they evolve. So which makes a very important key role in understanding the distribution of those stars and the universe also. So now here you can see we have different telescopes, okay, at different locations. Each of them have their own purposes. So this basically falls under high energy region. So where you have ultraviolet, X-ray, and gamma ray telescopes. Basically, you cannot observe these from the ground because ozone layer generally filter out the high energetic regime. So in order to study X-ray and gamma ray radiation, we basically go for space-based observatories. And along with that, we have infrared and optical too. And ground-based, most of the ground-based telescopes, which are mostly on peaks or hills, so they basically observe both in optical and infrared. And we have many prominent space-based telescopes like JWST, TESS, Kepler, Hubble, one of the good examples, Hubble. So most of them observe in optical and also some in infrared, some in partial, like they generally observe both in optical and infrared. Then coming to radio, radio is like more flexible. So there are different kinds of radio telescopes. Again, you have parabolic, you have Yagi, etc. So each of these can be used to observe a particular portion of the sky and throughout the day also. Like there is no restriction for radio telescope. Whereas in the case of optical, if you want to look at the night sky, you get a very little window compared to that of radio telescopes. So anyways, so each of these regimes have their own interesting things. So people who want to study pulsars, like say if they want to study AGNs, okay, so high energy spectrum, so high energy regions, so generally they go with all these three regimes. And we also generally, whenever we observe any binary stars which are like very, very, very active, in such a case, we generally observe for X-ray. Okay, if they are very active, we go for X-ray and ultraviolet radiation also. So that's how multi-wavelength studies are very much important, not just to understand about that celestial object, but also to understand their formation, evolution, and in turn the nature of, I mean, their distribution, and also about the universe. Now, yeah, along with telescopes, the next important thing, or like say the major, one of the major things in observational astronomy is detectors. So detectors plays a key role. So we have various detectors. Modern times, once upon a time people used to use photographic plates. Now we are using charge coupled devices and CMOS. So these charge coupled devices and CMOS are basically a semiconductor based on semiconductor chips. So they basically collect whatever the light which fall on them, and they convert it into electronic signals. So they are known to have quantum efficiencies as high as 90%. So compared to that of CMOS, CCDs are tend to have more, and they are very reliable. So the more the quantum efficiency. So whatever the light which falls on the chip, if majority of the light is able to kick out electrons or like helps in collecting electrons, so the quantum efficiency increases. Greater the quantum efficiency, the higher the sensitivity of the device. Okay, so once we get that, so once we have the light curve, so we analyze the light curve and then we try to interpret about the celestial object. But remember one thing, if you take any space telescope, they tend to have very, very, very sensitive devices. The sensitivity depends on high reflectivity of the mirror and also the quantum efficiency of the CCDs they have, charge coupled devices they have. Next, we have photomultiplier tubes. PMTs, though they are like very old, but still they are very helpful in detecting very faint light signals. So they amplify the photoelectrons, and they are still in use because in order to study gamma ray detection or like say Sharon goes, so they are like very helpful. Next, coming to bolometers generally used in infrared and submillimeter array of astronomy. So basically, whatever the radiation which falls on it, so whatever the minute temperature increase or rise will be there due to the absorbed photons, bolometers help us to detect that temperature rise. They are very sensitive. Now coming to proportional counters and scintillations. So basically the job of these counters and scintillations is to detect very high energy particles like X-rays and gamma rays, high energy X-rays and gamma rays. So how do they do that? They do it by measuring ionization or like what are the light flashes from the photon interactions which come. So these are like different instruments which are used with different telescopes. So being an observational astronomer in optical and infrared, basically we make use of CCDs most of the time. So and we collect the data using that. If you take the space telescopes provide you data with in terms of flux versus time or magnitude versus time. If you take example of test satellite, so test basically gives you data in terms of flux, electrons per second. How many number of electrons per second is detected is taken as flux, okay, and it is plotted over time. So whenever you plot light over time, you will get to know how light is varying, and depending on how is it varying, so we classify them into different types of objects. Okay. Anyways, we will be dealing with that in detail later. Then how to observe the sky? See, observing sky as an amateur is different. Observing sky as a professional astronomer is different. Okay. Now coming to observing sky, I'm strictly speaking about professional way. Okay. So what observational astronomers generally do is we generally write proposals, okay, to different national facilities, and we try to acquire time, telescope time. Okay. So in our proposal, we generally choose a problem. Okay, we choose one problem and we choose few objects to study and write a proposal. So once we submit our proposal, it undergoes a peer review. So based on the strength of our proposal, peer review may they allocate some nights, okay, for observations. I'm speaking about optical telescopes. Okay. So if you take radio, yeah, still radio may also the same procedure will be there. You will be allocated with some time. Accordingly, you can make use of radio telescopes. So once you write a proposal and once you submit, I mean, once you get some time, allocated time, then you can plan your observations accordingly. But remember one thing, better the problem, better the time you get. So it is very important to choose a right problem. Okay. Yes, in future sessions, surely we will be showing you sample proposals. In one of the sessions, we will be helping I mean, all of you to write proposals to national facilities. I mean, how to write proposals to national facilities and how to choose a problem and how to choose nights. Basically, we will be helping you with that. Don't worry, it will be dealt in upcoming sessions. Now it is just an introductory session. So I'm trying to give you a basic introduction. Okay. So write a detailed proposal. So you have to justify why you need observations. Okay, you have to include your time, how much amount of time you need for your observations, and followed by technical specifications because each and every telescope has some technical specification. What type of CCD they have. Okay. whether you want spectroscopy or whether you want photometry. Accordingly, you have to choose. Again, within photometry, as I mentioned, you have different bands, whether you want light in blue or red, okay, in any particular filter. So accordingly, you have to choose whether you want it in blue filter or red filter, or you want it in ultraviolet, or you want it in infrared. Accordingly, you have to uh, choose it. Okay. So please remember that. Okay. So now once your proposal is accepted, once approved, the observations are generally carried out in two main modes. One is classical observing, which is also called as visitor observing. So nowadays, this got like very dim. I mean, it became very less common because nowadays no visitor is going to observatories until unless it is very important for you and you want to go there. Okay, so most of the time it is done through what we call it as uh, from I mean, at the facilities, the technician will be there and you can do your remote observations. The other one is queue scheduled observing. So queue scheduled observing may generally what happens is whenever you have very prominent ground-based telescopes, like Keck telescope, VLT, and in the case of phase-based telescopes, Hubble and JWST. So there you submit your proposal, you are allocated with some time, and you will be in certain queue. Okay. So accordingly, you won't be like physically present there, but you will be receive the data after certain amount of time. Coming to the classical observing, you will be present at the site. You will be along with the technician. You will be collecting the data. Okay, it will be like real time. You will be in real time, and if you want, you can adjust exposures. So if you ask me what you prefer, I generally okay. Can anyone see my slides? Everyone can see my presentation, right? Yeah, okay. If you
Yes.
face any issues, let me know. So once your proposal is accepted, observation. So if you ask me what observation mode you choose, generally I choose classical observing mode only, visitor mode only, until unless if there is any issue. Like COVID may we have to choose remote observations. So at that time we have to opt that. But generally, if you have chance, if you want to go there, it's better to go there so that if you have any changes in the last minute due to some conditions or constraints, you can change your object. You can choose another object also, which is more aptable. So then once you collect the data, then you have calibration and data reduction. Okay. So what is calibration means? See, the whatever the data we collect, we call it as raw data. Raw data is unusable. You have to process it. So in order to process it, we do calibration. So calibration may we correct it for instrumental effects. So what are different instrumental effects? Electronic noise, detector imperfections, and sometimes you expect cosmic ray hits also. Vinay will be explaining that, like because during our observations we continuously see cosmic ray hits also. The source is unknown, but still they affect your spectrum, especially. We make use of calibration frames like bias frames, dark frames, fat field frames, and we calibrate the data. Once you do that, then you go for data reduction. For data reduction, we have different tools to do that. We have modern day tools like AstroPy and traditional tools like IRAF, PyRAF also. Okay. So once the calibrated data is available, it is then used to produce the final scientific product, such as a cleaned image, a flux calibrated spectrum, or something called as time series plot. So once you have your time series plot using different models, you have to model your time series plot and publish it. That is called as analysis. And once you do your analysis, you will publish it. Now I want to put a point here. So in our upcoming sessions, we will be helping you out with like how to write a proper proposal, how to choose a problem properly, okay, and how to choose different objects according to your problem statement. And not just that, so we can, like, if anyone of you interested to work on binary stars, we can provide you with some internships, like where you can support us, like where you can be part of our work, and you can also work with us on some binary stars. Okay, so where you get some exposure, okay, where you get some exposure on handling some data and all. Okay, so now let us move forward. Now, coming to the next part. So here we have something called a celestial sphere and coordinates, celestial coordinates. See, on Earth, if you take Hyderabad, Chennai, Mumbai, Pune, Kolkata, New Delhi, and all, so each and every city have some coordinates, right? They have their own latitude and longitude. Similarly, what astronomers do is, so we assume a celestial sphere around us, okay, on which all the celestial objects will be present. It's a huge imaginary sphere of gigantic radius. Earth will be at its center, and it helps us to map the positions of stars and other celestial objects, okay, as they rise and set. Okay, now you may ask, is it like real interpretation? No, it's not real interpretation. It is just for our better understanding. Please don't think that this is real. It is just for our understanding and for our better interpretation, for our mapping, for making mapping much easier. Astronomers make use of this celestial sphere. And like I mentioned, each and every city have some coordinates like latitude and longitude. Each and every star on celestial sphere also have latitude and longitude. Okay. So, and we call those as celestial coordinates. And there are various celestial coordinates, including alt azimuth. Okay. So, which is basically called as horizontal coordinate system. Then we have right ascension and declination. Maybe some of you already know it, which is equatorial coordinate system. Then you have something called as galactic coordinates and barycentric coordinates. Anyway, in upcoming, next I will be showing you making use of a tool, how to like search for an object, how to get information about object very soon. Now here, this is basically half of the celestial sphere. You can call it as hemisphere, and this is called as horizon. And all objects seems to rise and set, rise above the horizon and set below the horizon. And whatever the point which is exactly above the observer, we call it as zenith. And generally, stars rise and set. They appear to rise and set. Please remember. And here we have two coordinates. One is altitude. Altitude indicates at what height the object is for a local observer. And then the other coordinate is how far it is from the north. Okay. So there are two coordinates here. It's from right, from north towards right is one coordinate in this example. I'm telling about this example. And the other one is at what height it is from the horizon. So these two coordinates plays a key role. Yeah, one of the question, do all stars will rise and set? No, not all stars. Please remember, those stars which are close to pole star, Polaris, they never rise and set. I am speaking about all other stars which are farther from the celestial pole. Please remember it, okay? Those stars which are along, or like say those stars which are close to celestial pole, along just near to Polaris, if you take your place, let me say Hyderabad. So Hyderabad is around 17.5 degrees. So around 17.5 degrees, whatever the stars which are present close to the celestial pole, they never rise and set. They are called as circumpolar stars. They are always in the sky. Please remember. Okay. Those stars, other than that, they rise and set much farther from the pole. So here, whatever the coordinates I am showing you is horizontal coordinate system. They are basically altitude and azimuth. So astronomers make use of this horizon to define this altitude and also azimuth angle. Please remember, altitude is basically the angular distance above horizon, and azimuth is the distance measured along the horizon from a specific reference point. Like say if I'm taking north as my reference point, so it will be taken towards south, like whatever the angle it makes towards south. So accordingly. So as I mentioned, we have four different types of coordinate systems. Okay, one of them is equatorial coordinate system. So equatorial coordinate system may we have right ascension and declination. Right ascension is basically yes, exactly. It is true for the stars which are exactly other side also. I have taken northern star because we have North Pole. There is a star there, so it is easy to understand. Circumpolar stars can be on either side. Yes. So equatorial coordinate system. It has right ascension and declination. So coming to right ascension, basically right ascension is taken along the celestial equator. So you can see it here. And it is a 360 degrees one. So astronomers split it into 24 hours. So 1 hour is equals to 15 degrees in the sky. Okay. So exactly at vernal equinox. So you might have heard of spring equinox, right? So exactly at vernal equinox. So we have 0 hour. Then slowly, whenever you move towards the I mean, it depends again how you move. So whenever you move towards the June, like say summer solstice, it will be 6 hours. From there, again, it will be 12 hours. Again, then it will be 18 hours. So likewise, the RAE is from 0 degrees to 24 hours. Okay, so which is 360 degrees in total. So RAE is mentioned in number of hours. I will be showing you some examples very soon so that you will understand it, but much better. Then we have other coordinate system, which I have explained earlier, which is horizontal coordinate system. It has azimuth and also altitude. Altitude is basically height at which the object is there above the horizon, and azimuth is how from a particular reference point at what angle it is separated. Then galactic and barycentric. So barycentric means center of mass based on the center of mass of the system. Basically, we take barycentric coordinate system, and then we have galactic coordinate system. So galactic, the name itself says galaxy. Okay, so considering galaxy at the center, so whatever the measurements you do generally falls under galactic coordinate system. And you have heliocentric. Okay, so heliocentric too. So where sun is taken at the center or like coordinates. Next, coming to Julian date. Please remember one thing. In observational astronomy, to be specific, whatever the research we do, whatever the data we collect, it won't be in our general date. Okay. So if I'm collecting data right now, for example, so whatever the data we receive, okay, it is collected in terms of something called as Julian date. Now, what is this Julian date? Short form is JD. So this JD is very much important because in order to avoid conflicts in our calendar system, various calendar system, so astronomers have chosen a constant number, okay, which generally begins at noon on January 1st, 4713 BCE, and they started counting days from that particular time. So whatever the figure you are seeing, this number indicates that many days from that constant number, January 1st, 4713 noon. Okay. So now you may ask why we have to take such a figure? Why is it important? As I mentioned just now, there are like, it is for a better convenience for astronomers. Okay. So we have chosen this particular Julian date. Again, we have heliocentric Julian date, and then we have BJD also, barycentric Julian date. So we have various tools basically each of these tools help us in converting the regular date to JD or JD to HJD, JD to BJD. There will be a small variation, but it is like very important to consider it. Okay, right. Before that, I just want you to show something. I think that link was not working here. Okay, I think the link did not get attested to it. Okay, fine. So I just want you to show something. So whenever you go to internet, just go to JD to HJD or date to HJD. So it's very interesting because you have different tools to convert it. Say, for example, let me make use of, uh, there are many calendars or like there are many tools which are available online. So I generally make use of this Julian date converter. So here you can see. So here if you give any day or date, it will convert it to Julian date. So right now the Julian date is this much. Okay, with respect to UT, please remember it is UTC. So plus 5.5 hours gives you Indian time or whatever the country you are residing in. Accordingly, please correct it for. So this is the present Julian date. Okay, these many number of days are elapsed from January 1st, 4713 BCE from noon. Okay, so astronomers make use of JD in order to collect the data. So like I have mentioned, we collect light, right? So that light is plotted against time. The time is given in JD only. In upcoming slides, I will show you one sample data where you will understand it much better. Now, so how to target observation objects using seasonal constellations? Most of us are very much interested to just look at the night sky and we try to identify some constellations always. There are very prominent constellations in the sky, which you generally identify easily. Okay, they are very known to us. So this is for Northern Hemisphere. So as I mentioned, we have four seasons: spring, summer, autumn, and winter. So these are the primary anchor constellations. So you can find them clearly in the sky during these seasons. And based on these, you can plan your observations. So to make it precise, so in winter, the prominent constellations which you can see in the sky are Orion, Canis Majoris, and then you have Taurus. And for your reference, I have picked up one key star from each of these constellations. And this is their right ascension. So this particular object is at peak during that season. Okay. And this is declination, at what angle they are available. Okay. So now it is very important to know where you are exactly located. If you go to southern hemisphere, it will be different. Please remember. These things, I mean, these constellations, whatever I have chosen, it is purely based on northern hemisphere. Depending on where you locate, it changes completely. If you go more towards the poles, it will be completely different. So this is chosen for a typical northern hemisphere place like Hyderabad or like any like Indian city or like more of South Indian place. Next, spring. So spring May you can see these constellations and you have it here. Then you have more constellations in summer. Then you have your. So here you can see the change in the right ascension. Okay, so you can clearly see the difference. How much difference is there? Roughly, it is around. So here you can see this is around 6 hours, close to 6 hours. This is again 13 hours. So again here you have 20, 18 hours. So you have almost 0 hours. So based on this, you can pick your objects. So whenever you are writing a proposal, okay, which you will be learning in upcoming classes, upcoming sessions. So you have to choose objects wisely. That object should be available. That object should available in the sky, right? So it is very important to know which objects are available in that season. Accordingly, you have to choose your objects. So planning observations plays a key role. We should not forget that. Okay. So choosing objects, first of all, choosing a problem statement, then choosing certain problems to study is extremely important. Always remember. Okay, that plays a key role. Now let us explore something, making use of simple browsing tools. You don't need any extras, I mean, any additional software. If you have your computers right now with you, you can just go to browser. So I will show you some interesting tools, which we also generally use using, sometimes we use scripts, sometimes you use them directly. So if you have your computers right now with you, please go to browser. I just want you to introduce some new tools to you. Okay, so let us go to something called as airmass.org. Okay, just you can search in your Google airmass.org. Then that will take you to this particular website. Now, what is the purpose of this website? Now, this website gives you, based on your location or based on your observatory, whether that object is available in that season to observe or not. This is the right way to check whether that particular object is available or not for my observations. Is that clear? Say, for example, let me choose one object. Let's say, for example, I want to observe Proxima Centauri, or let's say Sirius. I will choose Sirius. I'm just taking it as an example. I'm not working on it. I'm just choosing it. So once you resolve it, so it will get you its right ascension and declination. As I showed you just now, RA and declination. So just go back to this table, which I have shown just now. Here I have shown that winter constellations में you can see 5-hour object, 6-hour object, and 4-hour object. Now, Sirius, what I have chosen, so is around 6 hour. Okay. Now, if you just scroll down, this is Sirius view. Now, here you have to choose your observatory. So, in India, like I have mentioned, there are various observatories. We have Himalayan Chandra Telescope, Indian Astronomical Observatory. We have Vainu Bappu Observatory. Let us choose Indian Astronomical Observatory. So I'm choosing Indian Astronomical Observatory here. So right after you choose it, it will give you very basic information related to that place right now, and it is chosen here. Can you see that? It got marked. Okay. Then just scroll down. Today is 26th October. Now Sirius is available. See, 30 degrees is like what I recommend generally. So 30 degrees and above, if that object is available, choose it. Like say, for example, Sirius is rising around 2:20. Local time is 2:20. That is 2 a.m. basically, 2:20 a.m. From there, it goes maximum of 40 degrees in the sky and around 4:40, and then it will slowly set. This is one example. Likewise, what we do is once we choose our problem statement, then we will pick up so many objects, okay, which are not studied. Please remember that object should not be well studied, because if it is already studied, what is the purpose of doing the observations again on the same well-studied objects? Of no use, right? So that is the reason you have to pick up such objects which are like less studied or neglected. Now you can choose another one. So any other prominent star, or if you want to choose anything, you can choose it here. So let me choose something called, right, let me choose something called as W Uma. This is another star in Ursa Majoris constellation. So now let us scroll it down. So this is that particular star. So here, whatever you are seeing, this view is 1.75 degree of the sky. And here you can see a circle around that object. Okay. If any one of you are using browser already, okay, in your computer, so you can just look at that object. If you can just zoom in and see. Okay. So this is your target object. Just scroll down. If you want to change observatory, you can change it, change observatory here, or else you can proceed and see whether that object is available in the sky. It is available, but after 1:50 a.m. only. Okay, so this is how astronomers basically make use of these simple tools, okay, to see whether that object is available in the sky or not. If it is available in the sky, we shortlist it, we write for proposals. Okay, so this is one of the simple tools where you can, if you are planning for any observations also with your own telescope, you can make use of this tool. Okay, any particular target, like say if you have any 8-inch telescope or 6-inch telescope with a good CCD, then if you want to do, because I have met a person who does his own observations. So like that, if any one of you are interested to do your own observations, collect magnitudes, then in such a case, this tool will be helpful uh, to check whether that object is available in the sky or not. Here you have so many options. See, here you have deep sky objects, solar system objects. If you know, if you have ID of any solar system object, you can provide it here. So it will search. And here you have multiple objects. So where you can give whole list of objects. So you can just type that objects, proper identifier, proper name or coordinates, and you can just upload it here. So it will give you a whole list of objects. Okay, if you have hundreds of objects to check, so it will give you the whole list. But generally, what I recommend is whatever the whatever you pick, basically like 5 or 6 objects, you can just make a text file and you can just upload it here or just drop them here. So it will search and give you what is their visibility. So this is one of such good tools. Next, in our observations, okay, so what we do is along with our proposal, we make a particular portion of the sky. Okay, so it is very important to know where your object exactly is. So this particular tool called as digitalized sky survey, DSS. It helps you to get the frame of that image where you can locate your object, whether it is exactly at the center or not. So to do that, what you can do is just choose whatever the object you want to do. So I'm searching Sirius here and just click get coordinates. So once you do that, the coordinates get updated here. Then the sky is partitioned into degrees, arc minutes, and arc seconds. So this is by default 15 by 15 arc minutes. Now I want you to see the difference. Now let us do one thing. So 60 arc minute by 60 arc minute is 1 degree by 1 degree. And then you can choose file format. I will choose GIF file. Okay. Then click retrieve image. Once you retrieve image, you will get 1 degree by 1 degree sky patch or frame, sky frame, where you can locate your object. Okay. So here it is. So this is 1 degree by 1 degree. Obviously, Sirius is like very bright here. Let us choose 10 arc minute by 10 arc minute. I want you to understand the difference here. Please remember, 60 arc minute by 60 arc minute gives you 1 degree by 1 degree. Okay. 10 arc minute by 10 arc minute I have chosen now. Just a second. Yeah. Okay, let me take 30 by 30 so that you can understand difference better. So this particular tool helps us to retrieve the image. Okay. So anyways, this is too gloomy. So let us pick some other object. Let us choose Proxima Centauri. So since Sirius is like very bright object, so let us pick something else. So here I am choosing GIF file and let me take 1 degree by 1 degree. So I think you know the size of moon and sun is half a degree, right? So this is 1 degree by 1 degree. So here I have chosen 60 arc minute by 60 arc minute. So which is 1 degree sky, right? So this is 1 degree by 1 degree. Exactly at the center, the object is Proxima Centauri. Now, if you want to go for smaller frames, sky frames, like you can choose 10 degree by 10 degree also here. So making use of these tools, what we do is we collect sky frames. So here you can see, this is like much more magnified version, right? Earlier I have shown you 1 degree by 1 degree. Now here you can see how, I think I have chosen 10 degree by 10 degree. So basically we choose 10 degree by 10 degree. Okay, so 10 degree by 10 degree frames are chosen and we highlight the object which we want to observe. Basically, if you give coordinates correctly, your object is exactly at the center of your frame. It should be exactly at the center of your frame. Please remember. So this is one more tool. So this tool helps you to check whether your objects are available in the sky or not. And this tool particularly helps you to take your sky frames for your observations. So that whenever you submit your proposal and once you get your data, once you get time to observe that object, this will help the technician to identify your object easily. Whoever the operator who is present there easily. Next, this is very, very important tool for astronomers. We call it as Simbad. So Simbad is like a good astronomical database where it will provide you whole information about different astronomical objects. Now let me show you by taking one example what all information it will give us or provide us with. So let me choose something called as Sirius. So I'm searching for Sirius. So here its identifier is Alpha Canis Majoris. Okay. So it's Alpha. Alpha indicates the brightest star. Canis Majoris indicates the constellation. So it is the brightest star in this particular constellation. It is classified as spectroscopic binary because it has another component called as Sirius B, which is a white dwarf. Now here you can see coordinates. Like I have mentioned, Hyderabad, Chennai, Delhi, all these cities have different latitude and longitude. Similarly, here you can see these stars have different coordinates. Okay, so here you call this as RA, right ascension. Then this is declination. Okay, so declination again goes from 0 to plus 90, 0 to minus 90. Please remember it. Next, here you have other additional information. Um, Probably like Vinay will be explaining you about what is parallax and all. I'm not going to touch it. Then you have spectral type. Most of you might have already heard like stars are categorized into different spectral types based on their temperatures or like you can say colors O, B, A, F, G, K, M. Okay, these are the different spectral types we have. O types are the hottest stars. M type stars are the coolest ones. Okay, M type stars typically have temperatures around 3000 degrees, whereas hottest stars, O type stars generally have temperatures close to 30,000 or 40,000. Okay. Then here you have fluxes or magnitudes. Okay. Now, just by looking at this, you can easily tell that this particular object is brighter in which particular region of the electromagnetic spectrum. So here you can see. So don't forget that these are in negative values. So smaller the negative value, you know how it should be, right? So these are fluxes basically. Okay, to avoid confusion, let me choose another object so that you will understand it much better. Let me choose Proxima Centauri. Yeah, here it is. Right here you can see. So here you have magnitudes. U indicates ultraviolet, close to ultraviolet. B indicates blue. V indicates visual, exactly at the center of the visual spectrum. R indicates infrared. RG indicates again RG, IJ, HKR, different infrared filters of different telescopes. Okay. Now you can clearly see that it is brightest in infrared region. Okay. So it is very bright in infrared region. So if you want to use an infrared telescope to observe Proxima Centauri, then obviously it will be a good target. So you should know whether your source is bright enough in that particular region or not. The same object, okay, the same object is not brighter in blue light. So if you use a blue filter and observe Proxima Centauri, what is the use? Okay, you may get some information, but if you want to know better information or like a very well deserved information, then obviously you have to choose that particular filter in which it is brightest. In this case, in the case of Proxima Centauri, you can clearly see that it is brightest in infrared region. Okay. And along with this, Simbad also provides you a good snapshot of the sky. Like, where is this object exactly? Okay. So this is also CDS, it is a DSS. You have two mass here and you have other sky photos where you can choose different things. So here you can see this is two mass. So depending on which region it is, accordingly that source will be brighter or not. Yes, brighter in the sense whenever you use different filters. Okay, so whenever we use different filters, so it appears to be very, very bright. So see here in this case. Okay, so if you look at this particular one, right here, this appears to be very bright, right? Can you see that? Here you can see that it is very bright. But if I choose DSS, here it is like very dim. Now, what is the difference? It means that in any other filter, whether it is blue or ultraviolet or visual, it is not that bright. It appears very dim. But if you choose infrared filters, then obviously it appears to be brighter. So that is the difference. So all of these stars, whatever you see in the night sky, they appear to be brighter in one particular region, I mean electromagnetic spectrum. Okay. So whenever you specifically know its temperature and whenever you specifically study that object or want to target that object, you should know in which filter it is the brightest. If it is a new discovery, it's a good thing. If it is already studied object, then it's better choose the brightest source and then proceed. Then along with that, Simbad also provides you with different identifiers. Identifiers are like names. Okay, each one of us have different names, right? Like we have our birth name, we have nicknames like relatives call us with some name, family will call us with some name, our friends will call us with some name. So likewise, each of these objects have official names. These are official identifiers. These are official identifiers given by different observing catalogs. Okay, so different observations. So common name is Proxima Centauri, but all other names indicate different observing catalog names or identifiers. Then here it will show you how many publications are there. So if you see for Proxima Centauri, there are 1442 publications from 1850 till date. It is extremely well studied object. Okay. Next, below that, you have collection of measurements and observing logs. So if you look at observing collection of measurements, it will give you what all measurements are done by previous authors. Okay, so it will give you velocities if available. It will give you distance. It will give you what type of object it is. It will give you its rotational period or orbital period. It will give you the composition of that particular object. So different astronomical measurements done by previous authors is provided here. So Sinbad is such a tool where you can still, here you have query, different query, you have criteria query, coordinate query, where you can give huge amount of, I mean, huge list of objects and get information about all the objects at once. Okay. So near future, uh, in upcoming sessions, I will show you how to make use of different different tools to such enormous number of objects, not just like simple each and every object. Since it is introductory session, I'm showing you individual objects here. But now we have so many tools where you can search for enormous list of objects. You can search 50 objects at a time, 100 objects at a time. Okay. So this is Sinbad basically. So Sinbad is such an astronomical database which gives you publications, which gives you common identifiers, which gives you basic information about it, and also various measurements done by previous authors. Okay, so this is one of the important tools. Next comes another important tool called as Vizier. See, please make a note of all these. Okay, if anyone of you are interested and want to continue for upcoming sessions or part of our internship, so then you have to make use of these tools for searching catalog, for searching objects and all. So what I generally recommend is, so just make a note of you if you are interested, so that it will be helpful. Not for at least for this work, maybe in near future if you go somewhere, it will be really helpful. Okay. Now Vizier is another tool which helps you to search for catalogs. So there are more than 25,000 catalogs available in Vizier. Okay. So where you can search for catalogs. Now you may ask, what are catalogs? Catalogs are like, it can be list of um, the data which is collected by a particular researcher, which includes their masses, which includes their times of minima, which includes various information related to a particular object or list of objects or group of objects. So if you want to study a particular object, you can just type a keyword here and search it. Let's say, for example, I want to um choose a cluster, and I want to study period luminosity. You can just put that keyword here and just say find. So whenever you do that, it will bring all the catalogs related to that particular keyword. Okay, so Vizier is such an astronomical tool which retrieves you with catalogs. For this also we have Astro Query where you can retrieve so many catalogs at once. Okay, but I'm still using traditional way to search and show you. Okay, when since you are doing it, though for those who are doing it for the first time. Next, we have a very important data archive, which is called as Gaia. So Gaia is very helpful for us, very important too. Mr. Vinay will be showing you how to make use of Gaia database to calculate the distances to a particular object. So this is a typical Gaia archive. So here you have different options at the top. Here you have home, search, single object. So you can choose search, and here you can search for that particular object. So here you can choose your target. Let's choose Proxima Centauri. And once you do that, just click on submit query. Or if you want to give any conditions, extra conditions can also be given here. So here, if you want to if you want to see only one particular information, here you can select and deselect it. And if you want to provide any additional conditions, so here you can give the conditions. Like if you want to have only parallax, if you want to see only parallax, so then you can choose all those conditions here and then just say submit query. So once you I think I have chosen something. Yeah, anyways. So if you just submit it, it will retrieve whatever the information available. And here you can see all relevant information related to that particular object, right from its magnitude, its radial velocity, its temperature, its parallax. Parallax is helpful in determining at what distance that particular object is. Okay, so here we have temperature. You can see that. So its temperature is less than 3000. It is a M-type star. So likewise, so Gaia, uh, this is a very basic information. Okay, so you can here go for advanced query, and here you can get the whole data also. Okay, but I am not going to show it you right now because in upcoming sessions we will be choosing some objects and doing that. So for now, I just want you to know that what does Gaia will give us. That's it. So these are some parameters that are provided by Gaia. So for whatever the object you are interested in, you can search it here and get the information. So till now, whatever we have learned is choosing objects is very important. So first you should have a proper scientific problem to do astronomical research, then choosing proper objects for your study, for your problem, I mean, to resolve your problem or to contribute to that particular problem. And once you choose the problems, you have to know in which season you have to observe those objects. So for that, you can make use of traditional seasonal constellations, or you can make use of different tools like this in order to get to know information about whether that objects are available in the sky or not. So what are the information I have shown till now is completely related to very basic astronomical things. Now we have other databases, okay, like NASA Exoplanet Archive. Then we have MAST portal. So MAST is also very important portal, like where you can retrieve data from Hubble Space Telescope. Okay, Kepler Space Telescope, K2. Then you have TESS also and JWST also. So basically, MAST is Mikulski Archive for Space Telescopes. Okay, so this will provide you with whatever the data which is available from a particular telescope. Okay, so before going to MAST, I just want you to show NASA Exoplanet Archive. So NASA Exoplanet Archive also gives you additional data, whatever is available for a given object. So many people think that NASA Exoplanet Archive is only for exoplanets. It is not so. You can also get additional information from various um, data archives. Okay, let me show you one example. Let me search for Proxima Centauri here. Why I'm choosing Proxima Centauri is it is very well-known name, so you can like easily search it and get the information. But generally, it is a very well-studied object. Don't forget it. Okay. So once you search that object and say search, it will take you to whatever the data which is available for that particular object. So here it is loading. It is taking some time, but yeah. So it will try to retrieve what all data is available for that particular object. So here you can see. So this is Proxima Centauri. Here you can see it. So it will show you what all information is available for that parameters. If there are any exoplanets, it will show you exoplanets. But my interest is, so here NASA Exoplanet Archive में, here you have something called as data. Okay. So once you click on data, so here you have Kepler, you have transit surveys. Earlier someone was asking about transit surveys. So here you have different transit surveys, and then you have other micro lensing. Someone was asking micro lensing. So micro lensing, we will also deal that. So there is something called as OGLE, which is dedicated for micro lensing only, gravitational micro lensing. We will be dealing it with that later. So here you have different um, types of data archives. One provides purely for exoplanet data, but others provide additional information also. So you can choose any of these and search for the data availability. So this is also one of the important databases where you have all list of surveys. You can click on any survey, search for the light curves. So I'm choosing randomly something called a super wasp here. Okay, so once you go there, you can search for that particular object. If you know its source ID, okay, you can search it here. If you have list of objects, you can upload that list also. Okay, say for example, you have hundreds of objects, and if you want to check if that if all that list have availability of data or not, you can do that by providing the list of objects also. If you have a single object and if you want to search for that particular single object, you can do this. Yes, exactly. Yes, whatever you said is true. So, so once you access any object, okay, you can make use of other tools which are available in NASA Data Exoplanet Archive. Here there is something called as under tools, there is something called as periodogram. Just go to periodogram in NASA Exoplanet tools. So periodograms help us to determine the period of that particular celestial object. It can be rotational period, it can be binary star orbital period, whatnot. So this is really helpful. Now you may ask, do you also use the same I mean, the tools like this? No, we don't use exactly this. But this is the way we have started initially. Then we have learned different tools. Okay, we got to know different other tools which will give us like more precise measurements. But this is also one of the good tools which give you precise periodograms because this works on various algorithms including box fitting, Lom's-Cargill, and Plavshan. So each of these periodograms work for different types of objects. Accordingly, how to upload your data here. We will be showing you all these in upcoming sessions. Okay. So since many people are like very new to these subjects, we are not like directly rushing into doing everything at once. We want to do it like step by step. So don't worry. In near sessions, I mean, in upcoming sessions, we will show you how to download the data. Okay. How to make use of that data to determine periods also. Okay. So this is one of such tools. And now coming to Master Portal, those students who are really interested to do their own research work, that too making use of space telescopes data, this is the right website or right database, or you can call it as data archive, where you can search your targeted object, get data from a space telescope, and work on it. It's really interesting one. It's very useful also. So whatever the object you have, whatever the target you have, you have to just search it here. Oh, sorry, Proxima Centauri, and just say search. If you know any particular ID, if you know Kepler ID, you can give Kepler ID because Kepler has its own IDs for all objects. TESS has its own IDs. TESS is another space telescope. It has its own IDs. Likewise, each and every space telescope and ground-based observatories have their own IDs. If you know that particular ID, you can provide it here. So it has brought us the data which is available around that location. Please remember, it brought us data around that location. Now what I do is, I will just left side my you have keywords and text filters and all right. Here filters you have. Just go down, then make the distance to be 0. So right after you make distance to 0, it will exactly precisely choose that particular object only. If you increase the distance, what happens is it will try to collect the data from nearby stars also. So in order to avoid that confusion, what we do, oh, sorry, sir. In order to avoid that confusion, what we do is we make the distance to be 0 so that you have your target locked. So once you have that, so here is our data. So this is from TESS telescope. So once you click on this time series, so it will display the data of that object. So it is loading actually. So yeah. So now some of you may ask me like, are there any easy tools to do all these? Yes, there are some tools which directly give you the data. But why I am showing each and every procedure is whenever you are really into scientific world, okay. So traditional methods are still concerned. Traditional methods are still respected because they help you to learn so many things. So from the past 1 or 2 years, okay, so from past 1 or 2 years, we are more into AI, right? From the past 1 year, we are much into AI. But before that, we used to explore by ourselves. We used to learn so many things. And all these things we got after searching a lot. So that is the reason what I suggest those students who are really interested to pursue research. Learn new things, okay, explore new possibilities, but also please keep that base strong. Okay, also learn traditional ways of exploring data, doing data mining. That helps you to learn so many things. That will help you to expand your horizon so that you can also what we call you can also like search for new problems. Like you can get rid of some problems by yourself. So here, if you see, I'm showing you the data of Proxima Centauri. This is from TESS satellite. Can anyone tell what is this? This is a typical flare, and Proxima Centauri is well known for its flaring activity. Proxima Centauri is our nearest neighbor. Okay, it has an exoplanet around it, known exoplanet, Proxima Centauri b. Unfortunately, this particular star is very explosive. It is like continuously, yes, so it is continuously flaring. Okay, since it is flaring continuously, so Proxima Centauri b might have like roasted continuously because these flares are extremely powerful. These are very energetic flares. Please remember, these are extremely energetic flares. So you can see the peak of these flares. They are very, very, very powerful. So here you can see another powerful flare. So these flaring activity, I mean, whenever you get the data precisely, you can understand the nature of that particular star. And not just that, you can understand what happens to the exoplanet which is orbiting around it. That too in the habitable zone. So yes, this flare, whatever we are seeing, is ejected by that star into the interplanetary space, I mean, or into interstellar. So that is a sudden eruption, huge amount of energy is released. Okay. And this indicates that that star is very active star. Okay. So this tool helps us to retrieve data of different objects. So if you have a list of objects and if you want to work on your own, so this is one of such websites. See, here I have chosen optical. Maybe near future, we try to bring different people from different regimes like high energy and radio also. Probably they will be helping those students who are interested in radio astronomy and high energy astrophysics. For now, we have chosen optical and infrared. Okay, please bear us. So likewise, you can search for different objects, stars. You can search for binary stars. You can search for different objects, and you can try to collect data. Once you collect the data here, you can model them and then you can proceed for publication. See, publication again is a crucial thing because most of the people think that publications come so easily. It's not so. So whatever the data we collect, we have to reduce it. We have to do data analysis and we have to collect additional data which is available online. Again, we have to do analysis on this, on that. Then finally you get a whole result and then you sit on those results for science. So writing science part is very crucial. Okay. So if you are good in science and good in technical part, it's really helpful for you. And if you are good in programming, it is extremely helpful so that you can do your job so easily. Okay. But sitting on science part, trying to interpret like what is exactly happening there is very much important. So whoever want to do some internships, what we recommend is, so try to learn right from basic, then slowly expand your horizon, build your basics strong. Okay, then try to pick some objects, work on them, write good science, try to identify some good results, do proper analysis, and then publish it. Publish it in a very good journal so that it will weigh your CV. It's not like you are going to publish it in any paid journals. Don't do that. I personally recommend you, whether you take some time, 1 year or 2 years also, still publish it in a good journal, peer-reviewed journal. Don't go for any unauthorized or, let's say, non-peer-reviewed journals. It's of no use. If you are really want to be a serious researcher, no one will encourage non-peer-reviewed journals. Please remember that. Okay, it's a personal recommendation and suggestion. So this is like what I want to show you and speak about. In our upcoming sessions, we will try to make use of some simple tools, Python-based tools, where we will show you to retrieve data. Once you collect the data, we will show you how to interpret that data, how to make use of that data. Some good peer-reviewed journals in India related to astronomy and astrophysics, which is related to India, Indian born is like JOAA, so or JAA, Journal of Astronomy and Astrophysics. So it is India based. I think it has more than one impact factor. So it is one of the good journals we have. So till here, like I thought of speaking with you. I will now hand over this. Uh, yeah. Okay. Anyways, I have shown you most of this. So now we have recently like the updated versions that is making use of a Python script using Astro query where you can directly download relevant data from different sources. This we will be doing later. Okay. So whatever I have shown you is very traditional, very basic, which I want you to learn and explore so that whenever you go to a real scientist or like real researcher, they will appreciate you that you have started right from basic, not directly jumping into the latest tools. Okay, right. Now I want to hand over this session to Vinay. So he will be explaining you the next part, the practical astronomy too. So he will be explaining you why pyraph is important, why we have to collect spectrum, um, why black body radiation is important, and what information can we gain from it. So he will be explaining that. So yeah.
Thank you, Ravi, for such a very basic, understandable presentation. So I'm
Yeah,
Vinay.
thank you.
Today, now I'm going to explain. Uh, so explain about how we can observe uh, stars using the telescopes and how we can use of them, means that how we can use that data for our science. Okay, right. So right. So usually I'm starting with the distance measurement. Normally, whenever we want to measure the distances uh, on the Earth, we can use meters, kilometers, like miles. These are the things to measure the distances in the on the Earth. But the thing is, whenever we are going to observe the stars, they are very, very far and they are faint also. Now, in that case, these meters are not enough because the numbers are very greater. Let's say the distance between the sun and the earth is 1 AU, it is nearly 150 million kilometers. So this is a very small distance if you compare the distance between star to sun. So in the case of the sun, it is just 150 million kilometer. In the case of the moon, it is just 3,40,000. It varies. Uh, uh, it varies. But in the case of the stars, it is very higher distances. Now, this distance measurement is started in the astronomy in something like before something 15 1600s, and it started with the Hipparchus. He started to measure the distances of the moon and the sun. And later, as we are getting a greater techniques, different techniques, we are going further. Means they developed a different kind of measurements, how to measure the distant stars. See, the what is the use of measuring the distance? Usually, let's say there is a light, and the light is at some 1 kilometer distance, you will not find much brighter. But when you're going to very near, then you can find it, and even you can tell the shape and how it is working. And in the same way, if you find the distance and you can measure their brightness, and you can measure the activity, as Ravi shown, there are some active stars. Continuously they are active. They send most of its mass into the space continuously. Now if you want to find such kind of mechanism, you require the distances. From the distances you can measure the brightness, and you can tell the mechanism, what kind of mechanism is happening. So now here we have the first one is measurement using the parallax. So here, let's say this red dot is our sun, and this is the earth. And we know the distance between the sun and earth is 1 AU. And every time, every 1 year, it will make one orbit around the sun. Now let's say this is a January, the time, this is a January, and now half of the year we are here. It's a June. Now I want to measure this arc second. See why I'm measuring the arc second. Usually in 10th class or something, we know how to find the distances and how to find the heights of some objects using the trigonometry. The same thing we are applying here, but here we need a longer baseline, because as we are going for the smallest measurements, very smallest measurement, you see here this is a 1 arc second. 1 arc second is a very smaller one. For that, here we have to go for the higher baseline. If we are going for the lower baseline, then we may get a very higher measurement. So for that reason, first of all, I'll start measuring a star's angle with respect to this longest baseline. Now I get some angle here, and after 6 months again I'll measure the same star. But see, as we are changing the position, the background will changes. Let's say if I'm observing the same star from here, the background will be different. Here I'll see only a 2 stars, right? And if I'm measuring from this side, I'll see 3 stars. So in the case of the parallax, the background is always constantly changes with respect to the observation. Now here I'll measure the angles, right? Here I'll measure one angle, here also I should get the same angle. Then only I'll take the half of angle, and obviously I will use the tan theta to find the parallax. Here the parallax, we will say distance is equal to 1 by parallax. Now here if you see 1 parsec means, how we can say this is an exact one. Let's say if a star is 1 parsec distance, then that angle is equal to 1 arc second. Now based on this, let's say if a star is having some 0.1 arc second or 0.2 arc second, so that the distance will be changed. Now this is okay to measure it from the earth, but the thing is, it is having some backlogs. So if you are measuring from the earth, you can measure up to 100 parsec, and after that you cannot measure, because the arc second become too smaller. It is going to 0.1, 0.001, right? So as we are going for a smaller arc second, the error will be more. So for that reason, we are going for the space-based telescope. Such kind of telescope is the Gaia telescope. Here, if you see, Gaia stands for Global Astrometric Interferometric Astrophysics. So here, I'll show how to find these values using the Gaia. Yeah, see this one. So this is a Gaia database. For example, here I want to find the parallax of of a star. Now I'll go for it, and then right. So here I'm going for the search, and here I'll give a star name. So as Ravi explained, let's say if you're going for the Simbad, so Simbad gives a right ascension and declination. So these are the right ascension and declination, or else here you have the name given to the star. So here I'm taking that star name, and then I'm using to write. So here, whenever you place the star name or coordinates, here it should come like this. LAN 360 is resolved by CSUM Starbuck or Simbad. After that, we will go for extra condition. Let's say here, if you see, there are many conditions. So we don't require all this. If you want to find uh, only the distance, here we have this one. See, so first of all, I'll take designation whether I'm getting the right source or not. And this is the source ID of the Gaia. And then here we have parallax and its error. So I'll go. So after submitting here, see this one. So this is the designation given by the Gaia. This is the name of the star in the Gaia instrument, like Gaia telescope. And see here, we have parallax. Parallax is nearly 2.42, something like that. And it's error. Now here, if you see MAS, see what is the meaning of MAS? This is milli arc second. It means it will go up to 0.001. See, that much accuracy we have. So by using the Gaia, at least 10 millions of stars can be found with a 1% accuracy, right? It's a small error, that is 1%. And after that, like if you are observing the stars out of the Milky Way, and if you are observing the stars some another galaxies, so the distance will be more, so that you will have more error. In that case, when we are observing more distant star, like the stars in another galaxy, the error will be something like 10%. But in the case of the within Milky Way, it will be only 1%. So now here we have parallax. This is in the milliarc second. Now I'll take that formula, and here I'll take, this is 1000 by milliarc second. See why I'm so this is a different calculation that we have seen here. This is the formula we have, but here we are observing in the arc second. So 1 arc second is 1000 milliarc second. So I'm converting them, so that here 1000 by milliarc second. Here I'll get the distance using the Gaia. And if you are seeing the same Gaia, here you have something. Yeah, for example, let's say here I have so I have a single object. This Gaia not only giving the parallaxes, but it can give photometric data as well as the spectroscopic data. So let's say this is a random star, and here we have parallaxes. This is a parallax of that star and its proper motions and everything. And after that, here it gives, see, this is a photometric data, different filters. Let's say it's a there are G filter, BP filter, RP filter. So based on what kind of studies we are doing, we will take this kind of data, and after that it will show the field, right? So after you're entering into the star name, it gives the field, surrounding field, the field of that star. As Ravi explained what is field and everything. So this is a field. So here we have the star. And after that, it also gives us the spectra. So now from this, what we can say is, here you know the distance, and you know the uh, photometric data, and also you know the spectra. From all these things, you can find its properties, like what is the temperature, and from the photometric data you can find what is the what are the mechanisms are happening on the surface of the star. And the next one is, yeah, so next one is the spectra, right? So now, sorry, yeah, if you see this one, this is a black body. So from using the black body approximation, we can find the temperature of the star. So here we have these three laws we have in our physics, right? So in the case of the Wien's displacement law, we can use this peak of this wavelength. Let's say if you see this 400 to 2000, this is in the nanometer, not in the angstroms. For example, see this red light is having peak here, and another light is having peak here. Now the peaks are different. If the peaks are different, then the temperatures also will be different. By using this formula, we can find the temperature of the star. And also using the Stephen Boltzmann, and here we can find it's how much energy is coming or how much luminosity is emitting, we can find. And also from the Planck's law, this is a main thing. The reason is, if you are using a lab black body, you will see a very smooth curves. But in the case of the stars, they are not smooth, because there we can observe uh, absorption and emission lines. So this is not that much smooth. So now, if I want to find, let's say this is actual spectra when we go to observatory, and after reduction, we will get this kind of spectra. See, this is not at all smooth. As I shown here, this is a very smoother one, but here this is not at all smooth. This is to be, and again, so whenever we are applying like Stephen Boltzmann or Wien's displacement, this cannot be worked. And Planck's can be worked for each wavelength. You can choose any wavelength on the spectra. Let's say here we have absorption line. For example, this is a H beta, or this is H alpha. Like that, there are many lines. So to find what exactly happening at a particular wavelength, then we'll go for the Planck's. So this is a one way to find the temperature, and there is another way to find the temperature using the multi-band photometry. For example, here I have this one. This is a OSA. So using this one, I can find the temperature of the stars. So here I'll show how it works. For example, here I have one star. Okay, so I'll choose this star. So I'm choosing this star here, and then this is a star I have, and then I'll check this one. So here we go photometry. So in this case, if you see the whole list, let's say there are hundreds of telescopes are available, ground as well as space. Now these are all the telescope filter. Let's say this is a galaxy, so this is in the UV filter. And after that, solar and digital sky survey, this is also U filter. And here we have B filter, G filter. Like that, different telescopes are observing a single source with a different filters. See, let's say whenever we use some colored kind of specs, right, then what happened, everything appears in a red color. Let's say if you're wearing some yellow color, then the surroundings appear in a yellow color. If you're using a red, surroundings appear like red color. In the same way, filters also works in that way. So whenever you are using a V filter, let's say G filter or some other filter, let's say a particular wavelength, so that I can observe that particular uh, flux emitted in that wavelength region. In that way, I can find all these flux values, and then see this one here, right? Here, these are all the flux values at a different wavelengths. So if you see this one, these are the all these databases, right? And after that, we will fit this data points using Yeah. So here I'm using a fit. Let's say there are many fits here. So here we have here, right here we have chi-square. So here we are fitting. So as I shown, okay, sorry. So as I shown here, here there are many points, and now I'm fitting all these points using our uh, library data. Like we have standards. Using the standards, I can find, means I'll fit the data to this observed photometric data. Now what happened here, I can find, so for example here, so after fitting, I'll go for this one. So here it is giving, so these are the ARIA and deck. And also there is one more point to be mentioned is here we have to give the exact distance. So first of all, by using the Gaia data, we can find the parallax, that is parallax. Using the using the parallax, we can find the distance. And after that, I am using some model. So here we have model, I'll show that model. And then here I am getting the temperature of that star and surface gravity of that star. So like that, there are many uh, fits are available, many. Let's say here, yeah, if you see this one, right? So these are all the libraries. So these are spectral libraries available on online. So using, you can use, let's say I'm using all this data, and then I'll start fit. Let's say I'm using this one. So here I'm giving the ranges. So I know my source behavior, so that T effective is from something like, so 1000 to something 10,000, and after that log G is this one. Like that, I will give the limitations for all these models, and after that I'll start fit. So when I fit, I'll get the, so here it will starting that, but it will take some time to give the result. It will not happens now. So here it will gives the chi-square and its temperature and its surface gravity. So by combining Gaia parallax and OSA, then we can get the exact temperature of the star. So after that, let's say, yeah. So now, so here we are getting the spectra like that. We are getting the temperature, and then what kind of instruments are we are using? As Ravi said, there are many instruments are used in olden days, but nowadays we are using the CCDs, charge coupled devices. They are very, very sensitive. See, we can have a doubt like this. See, we can use any kind of camera. Why we are going for this charge coupled devices? These charge coupled devices are very, very sensitive, and they are very, very smaller. The size of one pixel, the size of one pixel is nearly uh, 0.001 uh, micrometers, that much small, so that we can observe a very faintest objects. Like if you want to observe a supernovae, or if you want to observe novae, they will not be available as something like 1 magnitude, 2 magnitude, 3 magnitude. They will be a like in the range of 20th magnitude, 25th magnitude. So our normal cameras will not work there. So that is the reason why they are using this kind of instruments. In these cases, let's say when the photon hits this pixel, now it generates the electron, and now this electron will move towards, will move, and it create a image. Now this is an example of a CCD. See, each square is a one CCD. This CCD is used in the Kepler telescope. See, the price of one CCD is going into something like 2 lakhs, 3 lakhs. I'm saying a very small CCD. But in the telescopes, they will use a kind of CCDs. There, the price of each CCD, like 1.5 crore, 2 crore. That much price we are paying for the to observe the stars, to observe and understand the mechanisms happening in the stars. So in the CCD, first of all, photon observed, which is comes from the star, and then the charge will be, means the electron will comes out, and the charge will be stored here, and then charge will be transferred, and it create a signal. It can be converted into a signal. So based on that, we created a image. Now, this is a telescope. This is a VBT telescope. Usually, we take the observation from this place. There are other telescope, HCT, but most of the time we go for this kind of telescope. If you see this is a very big telescope, 2.3-meter telescope. See, this is a mirror. The diameter of the mirror is 2.3 meter. So it is a very, very bigger one. And here we have secondary mirror. So here they will open the slit, like open the gate. So when in the night time, they will fix this telescope fixed to a particular star of our interest, and the light falls on the primary and goes to the secondary, and again they will reflect back. Now if you see this part, this is the our CCD. So here we have CCD. So whatever the light coming from that star, that will be stored here, right? And after that, see what exactly happened inside the telescope. So this is a telescope, this is a VBT telescope, as I shown here, right? So these are the mirrors, and here we have CCD. So what happening before a light comes into the CCD? First of all, the light, the dome will be open. This is a dome, we call it as. The dome will be open, and we'll put our telescope towards a particular star, and then the light falls onto the mirrors, and finally it will go towards to the prism. First of all, as we know, when the white light falls on the prism, it will disperse. So let's say if you send this data to CCD, we won't get anything. So we have to make a finer lines. For example, if you see, we are getting the lines. Why we are getting the lines? Because we are using the grating. If we don't use the grating, then we don't get this kind of lines. And in the grating, we have higher resolution. If you are going for the higher resolution, then we will get finer lines. So here, grating, by using the grating, again we are diffracting, so that we are getting a more amount of that light as moving into a particular line, particular wavelengths. So here we'll put the CCD. So before going to the CCD, there are two things. One is prism and then grating. In some observatories, these two, prism and grisms, are attached as a single one, so that we can reduce the mechanics. So in this way, we'll get the CCD. And then here we have this kind of images, what we observe. So mainly we observe this five. One is a bias image, flat image, object, and comparison, and standard image. So this is a bias. So in this case, we will close the shutter of the CCD, and we will switch on it. Then this is just for a 1 second exposure. So whenever we are getting a frame like this, then only we'll start the observation, because these are all comes under the electronics. They are work with the electronics. So somewhere some part may be not working. In that case, we will see a dark color things. So, and in that cases, we have to remove that part, and then we will observe. So first of all, we have to see how our CCD is working, whether it is working fine or not. To check that, we need this kind of images in the biases. If we are not getting this kind of images, we cannot observe them. And after that, flats, there are other things I will explain in the later workshops, how the reduction and everything. But here I'm giving a glimpse of what kind of images we have. And if you see this one, this is the standard spectra using the FENE. We have lab spectras. So this is a FER or FENE. See, if you see, there are absorption lines. These are the black color. In our textbooks, they will give this kind of images. So they'll say this is a emission line and absorption line. The dark colors are absorption lines and the white colors are emission lines. Like that, we are getting a set of lines. So this is for to measure our main targets. See, this is our target. It's a stars spectra. Now see, if you see this spectra, a comparison spectra, in the comparison spectra, you have lot of absorptional image. But in the case of the star, we don't have that many absorption and emission lines because it depends upon the surface activity of the star. So here you see there are a few emission lines, and after that these are all absorption line. So this is how the CCD gets the image. And after that, and there is one more thing. See, as I said, we cannot use the cameras, right? Because if you take a picture, and obviously our cameras are made with a condition that it should capture the images when there is a light. See, if you have a light, we will get the good image. But in the case of CCDs, it won't be like that. So now the process is also different. See, if you take an image using a camera, you will get within a 1 or 2 seconds, you will get an image of yours. Means whatever the picture you are taking, you will get the image. But in the case of the CCD, it will take time. And also, this is not the last one. Means this is just a raw one. And then we have to use many mechanisms in between so that we have to get this kind of image. So for that, we are using some another uh, um, some other packages like IRF or PyRAM. And also these images are stored in a FITS format, not like a PNG or JPEG. So that FITS files can capable of holding each means a very simple data. Means the whatever the whole data we are getting, that whole data will be stored in a format, and it will be means it will be saved as a tables. Means let's say here you have this one. Let's say this one. Now I'm exposing the star for a 1 second. For 1 second, how many electrons are coming? Like that is what our flux. Now that flux is stored as a tables. Means the values will be stored as a tables. So FITS format can handle the tables with a higher efficient. That's why we use it in a FITS format. Now after taking this one, we need to uh, reduce to get the spectrum. Now for that we have IRAF, image reduction and analysis facility. So this one is given it developed by NOAO, National Optical Astronomy Observatory, in 1980s. So this is the oldest one, and even nowadays most of the people are using this IRAF. Even they are creating another kind of application that is totally based on the IRAF. So IRAF works in the backend, and whatever the programs that will be shown on the screen is works on the front end. But the backend, they are using this IRAF. So now this using IRAF, we can take a bias, dark, flat corrections. So whatever the images I said, we have to correct them. After correcting, here we will get our stars spectra. For that, we have to do bias, dark, flat field correction. So from using this photometry, we can find how much flux is coming from a single star at every time for a long term. So if you are observing for whole night, how the star is behaving, that can be given by this photometry. And spectroscopy, as I shown, sorry. So as I shown the spectra, that can be reduced using the IRAF. So this is a screenshot of the IRAF. See, in the IRAF, this is an old one created in 1980, something like till now it is something 150 years back. So they used a command line. So in the command line, we have to remember every command, and after giving, we have to do the correction. So here, if you see, here there are many packages for different ones. So this is the reason why this is a kind of hard thing. Nowadays, researchers, like new researchers, are going towards to the uh, like Python based application, because no one can, means most of the people cannot um, remember every command at every stage. For that reason, they are going for the Pyraph. Now, if you see this one, if you see the difference, see here, you have to give the command, then you will get a form kind of a thing, and then you have to fill it. But here, this is a GUI. By using Pyraph, so this is a Python based application GUI. So in the back end, the IRAF will be work, but in front end, it will show a tables like this. So it is a very easy to reduce the data whatever we got. In the future workshops, I'll be explain how this IRAF works, and then how to use this Pyraph. So this is the end of my presentation. If you have any questions, you can ask.
Yeah.
Yeah. So
Yeah.
just
Thank you.
uh,
Yeah. Yes, please. You can ask.
yeah. So I mean, I would just like to inform that in order to get the certificate, it is mandatory for the participants to fill the feedback form as just shared in the group. So please ensure that you guys, fill up that feedback form. It's very important for us to come up with the new sessions and improve the program so that we can serve the community better. And yeah, Raviji, please continue.
Yeah. If anyone have any questions, you can just ask us. I think there is one question in the comment section. Is IRAF necessary to run PyRAF?
Yes, it is. It is necessary. Without IRAF, Pyraph cannot work. So as I said, IRAF is working in the backend. Pyraph is just a GUI. It is based totally based on
Exactly.
the IRAF.
Yes. Some of the questions I have tried to answer in the comment section, most of them. If anyone have any questions like still remained, you can just let us know. And please fill out the feedback form so that like we can plan accordingly the next upcoming sessions. Yeah.
So anybody with any questions, you can ask directly.
Exactly. I'm
Just
just
to-
checking if I have missed any questions. Yes, anyone, if you have any questions, you can just let us know.
I'll just reshare the link. I just shared the link in the in the group. I'll share it again.
Yeah, the feedback form link is available in the group actually. Yeah, please, Yuvraj, you can ask your question.
Hello, can you hear me, sir?
Yeah, we can hear you.
Good evening, sir.
Good evening.
As in the last slide that you showed us, it was about a line spectra.
Mm-hmm.
It was a flat line. It was a horizontal line spectra. I was asking about that. What exactly was it showing? I could not get it.
Okay,
Okay.
just a second.
In the second session or first session, you're
No,
asking?
no, second session only.
Okay,
The
okay.
lastly have shown different spectra, right?
Right.
So
Okay,
in
I'll
one
show.
of them, he didn't understand the horizontal reason for
Yeah,
that
this one.
horizontal lines.
You're asking about this one?
Uh,
Uh,
yes, there
yes,
is a
sir.
horizontal line in the second
Bottom.
spectrum,
The
Yeah.
bottom.
the bottom one.
Hmm.
Yeah, he's
This
asking
one?
about like
Right.
what is the reason for that bright line, horizontal streak?
Right. Yeah. So if you see this spectra here, see, once it is like in the case of the photometry, they will totally open the that CCD's slit. But in the case of the spectra, they will not open totally. So this is the area that falls, means the light falls on the CCD. And now this one, this is a continuous. See, if you see the spectra here, right? So see this line is coming continuously, and in between we have absorption lines, absorption or emission lines. In the same way, it is like a continuous spectra, but continuous spectra, in the case of the continuous spectra, you have to be smooth, but in this case it contains both absorption and emission lines. So this represents the continuous flux coming from the star, but these lines are shown as a absorption or emission line. For example, if you see this one here, it is showing a continuous absorption and emission lines, but in the stars it cannot be happen. So that is the reason why some part of the star cannot be much active, so that you will see only a continuous flux, and some part of the wavelength can be active. That's why you will see these lines. So if there is no any kind of activity, you will not see these lines, you will see only this central line.
Continuous distribution.
Okay. I was just curious because this is the first time that I'm seeing a spectra or a spectral image which has a horizontal line, because most of the time we have only seen the vertical ones.
Right,
Mhm.
right,
Yes,
right.
yes, yes. This is actually whatever Vinay showed in his session at the last. Actually, the spectra which he has shown earlier is the actual published data he has taken. It is just he took it for your explanation. So whatever you are seeing here, so is basically this one, the actual data which we have taken.
Okay.
This is using this telescope. See here, you see you are seeing this telescope, right? So from this telescope we took this data.
Which observatory is this?
This is
If I may
VBO, Venubappu Observatory. It is in the Tamil Nadu. It is under the IAA, Indian Institute of Astrophysics.
Oh, okay. Thank you. And one more thing, where else are charge couple devices used? Because in our university we had that one thing which was used to detect, I think, radiations or something like that. My university is mainly for radiation studies,
Mm-hmm.
and
Okay. What?
they had this machine type of thing. Do they also use something like charge couple devices in there to detect radiations?
No, no, no. See what kind of studies they are doing first.
I mean, what type of radiation
What
use?
kind of
Can you like
studies?
be more specific? Because in our case, our radiation is basically the whole electromagnetic spectrum. We consider it to be radiation. So,
Okay.
can you be more specific? What exactly they mean by radiation studies?
So a part of the project was to shoot some gamma rays
Oh, okay.
into a brick which had some holes in it. So it was to study how much any material is absorbing the gamma radiation.
No, no, no. See,
Oh,
this
okay, okay, okay.
CCDs can be used from the UV wavelength, UV to infrared. But in the case of the gamma rays or X-rays, they will use the counters. So CCDs cannot be used.
Scintillation count. Yes, yes, yes.
Yeah,
That I have
CCDs
mentioned
cannot be
earlier.
used.
Yeah.
So that is the reason. So you might
For
not
high
use it.
energy, exactly.
You will use the counters there.
For
Okay.
high energy regime, you cannot use this. That's the reason I mentioned about counters and scintillations.
All right. Thank you so much.
Yeah. So if anyone have any other questions, please let us know so that we can answer those here. And please fill the feedback form. You can mention your interest there and all. Accordingly, we can like plan upcoming sessions so that like most of you can be benefited. If you do not have any questions, then I think we can end this session here.
Just one
So
thing, if I might
yeah,
ask.
you can ask.
So, in the upcoming sessions, we will be doing something related to coding as well, right?
See, in whatever the feedback form we have provided, you have to fill it up, right? So once you fill it up, accordingly, we plan our next sessions. So our goal is to train students accordingly, where we encourage students to write small codes, okay, where they write their own codes and try to retrieve data. Already existing codes are there, but we still encourage students to rewrite them so that they learn something new. So coding will be involved, analysis will be involved. Okay. retrieving data is involved, reduction is involved. So it depends completely on how many of you give feedback and express your interest for upcoming sessions. So accordingly, we will plan it. Yeah.
Okay, so it would be still helpful if we had a basic idea of Python or whatever language. Would it be Python or Fortran?
Python.
Mostly we use Python only.
Okay.
So yeah, because most of the astronomy tools you come across, especially in our field, we generally make use of Python. And for plotting and all, we generally use either Python or MATLAB most of the times.
The olden days, there is only Fortran language. Means they use
Exactly.
most of the cases in a Fortran, but nowadays people are converting all the codes into the Python for easy use.
Yes.
Yes, I was asking because in my university still they only teach Fortran and not anything like Python or something. So I was wondering
Okay.
if
Okay.
it's still relevant or not because it's really old, I know.
Yeah. Oh,
Yeah,
yeah,
but,
we can
but
understand
it
that.
is old, but if you learn them, you will understand the whole science.
Python also.
Whole
Yes,
science.
exactly.
Then you can easily write your own code based on what kind of packages are you are using, what kind of mechanisms are you are using. If you know the Fortran language correctly and whatever the application you are using, then you can convert into the Python. So it will
Yes.
be easy.
It will make it it will be more easier actually. Whatever the language you learn, whether it is C, C++, Java, whatever it is. So coming to the application part, whatever the new languages come up or like new things come up. See, MATLAB, no one helped us to learn, right? So
Mhm.
once we are into PhD, when we got these new plotting tools, so we have learned it on ourselves because we have very little programming knowledge by then and no idea about MATLAB, but we still explored. We started writing some basic codes, plotting codes and all. Then that's how we got exposure. So the same happens with you also. Need not worry. So the Fortran will be like a basic for you. So where you can explore Python. So there are many Python free classes are available. So you can whenever you get some time attend them. So try to understand the structure of that language. So you will like it actually.
All right. Thank you so much. This
Yeah,
I was really confused about this.
yeah.
Okay.
Yeah, can
Thank you.
understand. Yeah, it's okay.
So, any more questions?
One question Padma Priya Nair asked, why do we give different identifiers instead of one standard one? See,
Nice
the
question.
answer is very simple. Let's say uh, in our language, let's say in Telugu, we will call water as a manchneelu, but in Hindi it is pani, like that. So different people are using their own scopes, their own telescopes. For that reason, they will give a
Catalogs,
different
yes.
names. But their right ascension and declination both are same, but they are giving their own name with a telescope.
So whenever a telescope observes or like plans to observe the night sky, it will just collect the star. I mean, it will list out all the stars, okay, and it will give their own identifier. So it's like the target telescope, whatever it is. So they have their own catalog. So you have Kepler input catalog. You have TESS input catalog. Similarly for JWST, similarly for other sources like Gaia, he has shown like the source ID. So each and every telescope or observing catalog, I mean each and every observing facility, they sometimes have their own catalogs. So that's the reason you see so many list of identifiers for the same object. So all of them are scientifically recognized.
Yeah, and Saroj Saho, why do astronomers using CCDs for imaging often stack multiple short exposure instead of a single long exposure, and how does this tech impact signal to noise ratio in faint object detection? See, the stacking of images are used for the astrophotography, not for the normal research observation. But in some cases, let's say if you are observing the spectra, then you can stack them to understand, to increase the signal to noise ratio. But if you are giving the longer exposure in spectroscopy, we will give longer exposure up to 1 hour. But in some cases, what happen, the CCD is overexposed, so that the whole observation will be it will not be useful. That's why we can give a higher exposure, but we cannot give greater than 1 hour. So our CCDs are that much sensitive, so that we cannot give. We always try to give a less exposure in the spectroscopy, then we will stack it. But in the photometry, we always give a very less exposure, like 30 seconds. If it is a faint, they will give. We can go up to some 2 to 3 minutes, because that in the case of the spectra, you will use a very small part of the CCD, but in the case of the photometry, you are using the whole part of the CCD. So in that case, if you are giving higher exposure, that whole frame will not be useful for our studies.
Yeah. And Kamal, yeah, like you have said, most optically fiber based. So are any left in India where one could see through eyepiece in a big observatory? It's a really interesting question. Because see, most of the observatories, whether it is VBO or Indian Astronomical Observatory, IAO, or Mount Abu telescope, whatever it is, they are scientific, and generally they are, like you said, yes, they are connected to fiber optics, and there will be a CCD there. You can put on, see, there are some facilities where you can still put an eyepiece and look through it, but the observatory's time is like really precious. And I don't know how many of you heard of it or not. In order to run one session, one night, like the observation session, it will cost around some lakhs, right? Some lakhs of rupees to run that huge machine. So obviously, the time we generally get from each of these national facilities is very precious for us. We try to make use of that time very cautiously. We choose objects so cleverly, and we try to get as much amount of data as possible. So we cannot like misuse that time, right? So there will be some places maybe in near future, once those places are like no more useful for astronomical observations, maybe I think they will be open for public, where they can look at those telescopes, look through them also. But probably for now, whatever the active observatories which are there, so it's not an easy thing to run those telescopes. It is like pretty expensive, so we cannot misuse that time. So it is very important for us to collect the data rather than just looking through an eyepiece at some object.
And one more thing is, this telescope's mirror diameter is very high.
Extremely large,
So
yes,
in this
extremely large.
in that region, you will see a very smaller field. So if you are seeing a moon through the telescope, you will see a very small part. You will not see the whole moon.
Exactly.
So even if you see through them, you can't get see, if you see through some 4-inch, 5-inch, you will see the whole moon. But in the telescope, you can't see. Even if you see through the telescope, you will not feel much better.
Until unless it is a like very dim object or a dim comet or something. But it's still a questionable. So I don't think observatories will now permit anyone to just look through eyepieces.
No,
So they are more of scientific instruments. So we cannot like use them like a regular ones.
But in some cases, this IA, they will let's say there is a eclipse, or there is some other kind of things. If there is anything, they will use.
Transits.
They will publicly live to see the things, but not through the scope, but through the cameras.
Yes. Through the cameras, yes, not through eyepiece directly. Anyways. Yeah, but nice, interesting question that is. Yuvraj, you have some question. The angular field of view matters a lot in clicking these pictures, right? So yeah, field of view is obviously very much important. Like I have shown the difference when you take 1 degree by 1 degree and half a degree by half a degree, or 1/10 of a degree by 1/10 of a degree. So it's very important. So yes, that plays a very like key role. So it's very important. Yeah. How can Python-based tools such as AstroPy and CCD Proc be optimized to handle systematic noise in large-scale CCD imaging data sets from telescopes like Rubin Observatory?
Rubin. I don't know exactly about the Rubin Observatory, but in our studies, we use usually this AstroPy and CCD Proc. See, usually this CCD proc is coming again. Again, it is coming from the IRAF, which is in the Fortran, and this AstroPy can be used to create an application like that and optimize. You are asking about the optimization. See, signal
Yes.
to so here what yeah, systematic noise. So systematic noise can be removed using a IRAF. There are different mechanisms. Means what kind of mechanism to be used to remove the noise, and everything can be included in the IRAF. That can be solved using the IRAF. But I don't know much about Rubin Observatory, but they also have the same thing.
I think most of the international facilities still have um, or still follow the old traditional, I think the same
Yeah,
things.
they are all old tradition because
Yeah,
they have started it something 50 years, 100 years back. So
exactly, exactly.
if they want to use this one, they may not be match. They
Yes,
may not work
exactly.
well. So that's why they will not change their systems. They will always
Yeah.
use the same
But
thing.
and sometimes what they do is in such observatories, they go for robust calibration and they sometimes go for advanced imaging combination methods and precision masking strategies also. So there are like various strategies like where you can cut down like whatever you have mentioned the noise systematic noise. So there are various strategies and there are like algorithmic strategies also like AstroPy may you have CCD data and where you can keep all metadata and systematic noise flags okay throughout the reduction process. So yes, there are some possibility strategies are there, optimization tools are there. Yeah. Uh, would we be having mentor sessions or can we ask you simply in the group? क्योंकि it would be great if you could guide us a little bit towards the career paths we have, or we would have most probably. See, if you have any questions related to your career or like say research related, you can like DM us anytime, whether it is me or Vinay or Nitesh ji anytime. Like whatever possible for us, we will always guide you. Okay. Because so many students will contact us, so we are always open to encourage and support you. So whenever you want have any questions related to anything, you can just ping us, direct messages anytime, not an issue.
Yeah, so we are here to like literally train the next gen leaders of science, and we would really like all of you to do groundbreaking research. And we are always there, and that's the entire motto of doing this initiative. That we do this uh, very strong mentorship, which is very feedback based and very personal, so that we can help you improve upon based on where you lack and possibly achieve your research goals. So yeah, we're always there, and we'll keep doing such sessions.
Yes.
And
And one more last question. I think Kamal was asking that question, I think more than two times.
yeah,
So see, HJD is basically it corrects the Julian date with respect to the Earth's position relative to heliocenter, I mean Sun's center. Okay, so it will assume Sun as a fixed reference point. I told you, na, heliocentric, so where Sun is fixed as a reference point. Whereas BJD, barycentric refers center of mass. So center of mass of what? All solar system bodies. So in the case of heliocentric, Sun is assumed to be a fixed reference point, whereas in the case of barycentric, barycenter is fixed because it gives you a more stable and proper frame of reference. So barycentric means center of mass is taken basically. That's it. That is the key difference actually, conceptual difference. So yeah, that's the answer. Yeah, finally, I think we can end this session here. So thank you one and all for having so much patience and attending this session. So if you have any questions, any queries related to anything, you can ping us anytime on WhatsApp or LinkedIn, wherever possible. We will try to answer your questions and we will try to support you always because whatever the support we did not get when we were like in your age.
exactly.
So now you have so much opportunities and possibilities to connect so many researchers throughout the world, thanks to social media and platforms like LinkedIn. So we are always ready to help. So we don't want you to face the same things what or difficulties we have faced. So that's the reason, one of the reasons we have started Astro also. So yeah, all the best everyone. So please fill the feedback forms in your free time and let us know your interest. So we will meet in our next session. So thanks to Nitesh ji and Vinay
Thank you, Ravi.
for your support.
One
Yeah.
last thing, I
So
would really, would like to thank Ravi ji and Vinay ji for taking out their precious time and to inspire you all. And most importantly, this one last thing is that as a budding researcher, we should all learn to ask good questions, because the research is all about asking good questions. And most importantly, given the data coming from James Webb, trust me, this is the most interesting time to be a professional astronomer and astrophysics. Things are going
exactly.
to be on its
One,
head. And
one of the best instruments in
yes,
the whole world.
yes, and there is so much that is going to be discovered, that is going to be beyond how we understand astrophysics.
Exactly.
The rules are going to
Exactly
be
true.
broken, so that's going to be very interesting. And as Vinay ji was talking about Max Planck, so when Max Planck entered physics, he was advised against entering physics when people said him that everything has been discovered in physics and it's not a right time to enter physics. And then the quantum mechanics was discovered, and he came up against the problem of black body radiation, which was
So true.
the contemporary physics of his time was unable to explain. So this is the same time, I guess. And so that's why we are here to help you become one of the best version of yourself in terms of research. We are here and we'll keep doing such sessions, and make sure you do your best. You are sincere towards the craft, you enjoy the process, and you are there to learn as much as possible. So thank you,
Yeah.
everyone. Again, please do fill up the
Yeah.
form. That's really important.
Yeah. Thanks
Thank you,
everyone.
Ravi.
Have a great night. Yeah. All the best. Take care. Bye.
Bye.
Thank you, sir.